Hello students, in last class we already discussed that what is series LCR circuit, how to find out impedance of a series LCR circuit, and what is the natural frequency of the series LCR circuit. That is, if we use all the components, the resistor, an inductor and a capacitor all in series in a circuit which is connected with an external alternating EMF source which will provide an EMF E equal to E naught sin omega t. Then if the resistance is R, inductor of inductance L, capacitor capacitance C, the current I. So we know if E equal to E naught sin omega t, so within this circuit the I will be how much? I equal to I naught sin omega t minus phi. We already studied about it. And what is I naught? I naught equal to E naught by Z. This implies I naught equal to E naught by Z. What is Z? Impedance. That value equal to R square plus XL minus XC whole square under root. And I naught will be I naught maximum when Z tends to Z minimum. What is the value of Z minimum? Z minimum equal to when XL minus XC whole square will be equal to 0, or this implies XL equal to XC, or we already calculate that the frequency omega equal to 1 by under root of LC. This is the value of frequency only when the current flowing through the circuit will be maximum, and this frequency is known as what? Natural frequency. And from this is the angular frequency, and from this we can calculate the linear frequency will be equal to 1 by 2 pi root over of 1 by LC, or simply 1 by 2 pi into 1 by root over of LC. This is as omega equal to 2 pi f, so f equal to 1 by 2 pi, so just multiply by 2 pi. So this will be the natural frequency of the LC given LCR circuit. So at any instant when the supplied EMF will provide an frequency omega which is equivalent to this much, at that instant there will be electrical resonance, we already know. And when electrical resonance happen in a LCR circuit, that circuit is known as resonance circuit. So when the applied EMF will provide a frequency which is equal to the natural frequency of the given LCR circuit, because in each LCR circuit we have an inductor, a capacitor and a resistor. Resistor is independent of omega, but L and C, both the inductance and capacitance, both are depending upon omega. So according to the value of L and C we can able to calculate or find out the natural frequency of the LCR circuit. So according to the natural frequency of the LCR circuit, if the output potential EMF is able to provide a frequency omega equal to 1 by under root LC, then at that instant for the output source E equal to E naught sin omega t, the current will be maximum and it will become a resonance circuit. Clear? So if that particular frequency where it will be equal to 1 by root over LC, let it be denoted by omega naught. So when the output frequency is equal to omega naught, the current flowing through the circuit will be maximum and it will become a resonance circuit. So if what will omega naught? So when the output omega is equal to omega naught, then we will get what? XL equal to XC, because when omega equal to omega naught, XL equal to XC, this implies Z equal to how much? R square plus XL minus XC whole square under root, which is equal to only R because this tends to 0 as XL equal to XC. So this implies we will get I equal to how much? I naught equal to E naught by R, the maximum value of I naught when omega, the output frequency, is equal to the natural frequency of the LCR circuit. But if omega is greater than omega naught, the output frequency omega is greater than the natural frequency omega naught, then we will get what? XL is greater than XC, as XL is directly proportional to omega and XC is inversely proportional to omega. So if omega, the applied frequency, is more than omega naught, then XL is greater than XC. So this implies XL minus XC whole square will increase because XL minus XC is a square term. So if XL greater than XC, so XL minus XC square will increase. This implies Z will increase. So if Z will increase, I will decrease. Clear? Again, if omega is less than omega naught, here omega is greater than omega naught, here omega equal to omega, then we will get I maximum. This is maximum value of current. If omega is less than omega naught, I naught will decrease. If omega is less than omega naught, then XL is less than XC. So this implies XL minus XC whole square will increase, and this is a square term. This implies I naught will decrease as Z increase. When XL minus XC whole square will increase, it will cause to increase the impedance. As impedance increase, the current value will decrease. So for only one value of omega, applied omega, that means when omega is equal to the natural frequency of the LCR circuit, then only we will get maximum current through the circuit, and the circuit will become a resonance circuit. But when omega, applied omega is less than that of the natural frequency or greater than that of the natural frequency, in both these cases the current will decrease. So if we want to plot a graph between the frequency and current in a LCR circuit, so it will be like this. If along this direction I am taking omega and along this direction I am taking I. Clear? So let it be some values, omega 1, here omega 2, omega 3, omega 4 and omega 5. There are certain frequencies, and among all these frequencies, if omega 3 will be equal to the natural frequency omega naught of the given LCR circuit, these are the different values of the inputs. Here I have a source of value omega. So in place of omega, I am using another source which is having frequency omega 1, omega 2, omega 3, omega 4 and omega 5 and so on. So there are a large number of inputs from which you are getting different values of frequency. But for the given value of omega 3, which will become equal with the natural frequency, then only if omega 3 is equal to omega naught, so at this particular input of frequency we will get what? Maximum current through the LCR circuit. So at this point the current will be maximum, because here the omega 3 is equal to omega naught. Okay, and for omega 2 again we decrease. If we decrease, omega is less than omega naught, current will also decrease. So for here current will be like this. Again for omega 1 current will be like this, and so here again omega 4 current will be here, omega 5 current will be here. So if we plot the graph, it will look like this. The graph will be like this. Okay, so for a particular value we will get what? The maximum value. Then for other frequencies the current value will be again decreasing like this. Okay, if we want to make omega 4 equal to omega naught, we know what is omega. Omega naught equal to LC, 1 by under root of LC. Accordingly, if I am changing the value of C, so the value of omega naught will change. If I am decreasing value of capacitance, omega naught will increase. If I will increase the value of capacitance, omega naught will decrease. So we can adjust omega naught. If I am adjusting the omega naught of this LCR circuit, so that its value will increase and it will become equal with the value of omega 4. Okay, that means I am decreasing the value of capacitance which is using here, so that the omega naught value will increase and it will become equal with the value of omega 4. Then when it will apply to the circuit, what will happen? It will give us a graph like this, because at here omega 4 it will become equal to the natural frequency omega naught. So from omega 4 we will get the maximum current. So the graph will be like this. Because for omega 4 the current will be maximum here. Clear? So for different input values of the frequency, if we make the input value equal with the natural frequency of the given LCR circuit, then for that particular frequency we will get maximum current, and for a below and above that frequency we will get less amount of current. So this particular case, when the input frequency becomes equal with the natural frequency of the LCR circuit, it will call resonance, and at this place the value of current will be maximum. This is I naught max. Clear? And the maximum value of peak value of current will at this place only. So this will get more power because power is I square R, so it will get more power, and the power and the current which is near to this, it will also get some power, this will also get some power, and similarly the power range will vary up to 0.707 I naught. So up to this much range, all the frequencies lying within it will get improvised and they will gain some power. So from maximum value to up to the value of 0.707 I naught, all the frequencies those are lies within this range will improvise and get maximum power. That's why this much length of the frequencies is known as the bandwidth of the given signal. Okay, if for omega 3 the current is maximum, then for that particular frequency this will be known as what? When the current will be 0.070 I naught, this much length will be known as the bandwidth of the given signal or the particular frequency, which will be omega 3, and this bandwidth, all the frequencies lying in this bandwidth will get improvised and they will get the maximum powers. Clear? That's why the separation between two different signals will be beyond the value of this bandwidth, so that there will be no noise pollution in the signal. If all these frequencies get more improvised, so we will get some noises. That's why this length will be very small. So how we can decrease this length, or how we can decrease the bandwidth of the given particular signal? So for this particular case, when omega naught is equal to omega 3, we will get the maximum current at this place, and this is the resonance case for omega 3. So if here omega 3 equal to omega naught, that means omega naught equal to LC, so XL equal to LC XC for this omega 3. So what will be the value of I? So at this particular case, when omega 3 equal to omega naught, so here you can get omega 3 equal to omega naught, so XL equal to XC. So what is I? I equal to E by Z. This implies I naught equal to E naught by Z, or we can write I naught equal to E naught by R, because Z will become R when XC equal to XL. So for this particular case, if I am decreasing R, I naught will increase further. Clear? If for this particular case I am decreasing the value of resistance, because when XL will equal to XC, Z equal to R. So when we decrease R, Z will decrease. If Z will decrease, I naught will increase. So here already we have maximum value of I naught. But if for the given case, when omega 3 equal to omega naught, I am further decreasing the value of resistance in the LCR circuit, then the current value will increase, and here for the omega 3 the graph will become more sharper like this. Okay, this current will increase like this. And now if this is the value of I naught maximum, so again we know for up to 0.707 I naught the frequency will get improvised. So 0.07 I naught will be this much for this now. So now the bandwidth will decrease up to this much length. So the noise will be less, because this will be 0.707 I naught max dash if this is I dash. So the bandwidth will now decrease and the noise will be less. Clear? So this will determine the quality factor of the given LCR resonating circuit. Clear? If the bandwidth will be very less, the noise will be very less, and the clarity in the signal will be more, or the quality of the signal will be more. That will depend upon what? The quality factor. So quality factor is depending upon what? For a particular frequency which is equal to the natural frequency, we will get the resonance circuit, and for that resonance circuit, if we will decrease the value of resistance, we will get more value of the current, which will give us less amount of bandwidth, so that there will be less noise within the signal. So what is quality factor? quality factor is known as when for a resonating circuit XL equal to XC, that means the potential difference across inductor and potential difference across capacitor will be same, because if XL equal to XC, we know what is the potential difference across inductor, it will be equal to I into XL, and potential difference across capacitor will be I into XC, and we already know in a series circuit I is same, and for resonance case XL equal to XC, that means VL equal to VC. So potential difference across inductor equal to potential difference across the capacitor, and both are in opposite phase. So from the impedance triangle we will get what? They will cancel each other, because as here we already know that this is the phase diagram. Here is the current I and VR, here is VL, and here is VC. So if for when resonating circuit will match VL with VC, so VL equal to VC, so these two will get cancelled, so we will get only VR. So potential difference across the resistor will become the input potential, so we will get E equal to VR when VL equal to VC or the circuit is resonating with the given LCR circuit, or in case of resonance we will get the total input alternating EMF will be equal to the potential difference across the resistor, because these two will cancel each other. So if we are taking the output signal here, if this is the output signal across the capacitor, so this signal, this potential difference will how much in comparison to the input potential, that will gives us what? That will give the quality factor, because quality factor depends upon how much amount of current we will draw from the given circuit, and current will depends upon as these two will equal. If the potential difference will be more in comparison to the input potential, so that's why we will get the more power, and more power will increase the more current. So the output will how much? So the quality factor will be defined as the potential or voltage across L or C, because in this particular case when the circuit is in resonance, the potential difference across inductor or potential difference across capacitor both will be same, because VL equal to VC. So the voltage across L or C divided by voltage across resistance, because we already know in resonance case the voltage across resistance is equal to the input voltage. Clear? So quality factor for a given LCR circuit is defined as the voltage across the inductor or capacitor. You can choose across which you are taking the output, or if you can choose capacitor, or if you can choose inductor. So voltage across the L or C divided by voltage across the resistor, or this is known as what? The input potential or input voltage. So it will become how much? So we know what is voltage across L or C. You can choose one of them. If I am choosing here capacitor, so it will become I into XC divided by voltage across resistor I into R. So I will get cancelled. So Q factor will become XC divided by R. So what is XC? XC equal to 1 by omega C divided by R. So from this we can write Q factor equal to 1 by R omega C. This implies Q equal to 1 by RC. What is the value of omega in case of resonance? Omega equal to 1 by root over of LC. Clear? So this implies you will get what? The quality factor equal to here it will be XC equal to 1 by omega C. So 1 by omega C equal to 1 by omega C divided by R. So this will, so omega equal to how much? Sorry, here 1 by RC, omega equal to 1 by root over of LC. So it will become root over of LC. So Q factor will be equal to 1 by R into root over of L by C, because 1 root C root c will get cancelled, so this will become how much? This is known as the quality factor of a given LCR circuit. So from this, if we will increase R, Q will decrease. If we will decrease R, Q will increase. Or if we will increase C, Q will decrease. Or if we will decrease C, Q will increase. So as shown here, for the particular resonance case, when omega 3 equal to omega naught, I am further decreasing R. The quality factor will increase and the resonance circuit will become more sharper, so the bandwidth will decrease, so there will be less noise in the given signal and the signal will be more clear. And this particular circuit will be used in the electronic device like television in our day-to-day life. And these frequencies are the different frequencies supplied by the different channels in our television or in our connection that we are using the DTH, direct to home service. If omega 1 is response for a one given channel, let it be for star, this will be for G, this will be Sony, this will be for the BBC, and for different channels have different frequencies. So when we choose one particular channel, at that case the LCR circuit which is used in our television set, it will adjust its natural frequency to the frequency of that particular channel, so that that particular channel will get improvised and it will attain maximum current. So we will get the sound and picture of that particular channel. And if we want to adjust that particular channel, its volume, its clarity or its color, then we will again change the resistance of the LCR circuit for that particular resonating circuit, so that it will get more sharper and the sound and picture will be more clear. So the LCR circuit or the resonance circuit is used in a television to tune it. That's why this is also known as tuning circuit. So a resonance circuit is also known as tuning circuit because it is used to tune the signal. Clear? So you already know what is quality factor. So for a particular resonance case, I am getting the maximum current, but the frequencies which lies up to 0.707 of the maximum value of the current will also get improvised. That's why there will be a large number of frequencies we will get which will create noise or disturbances. So if we want to decrease the disturbances, we have to again improvise or increase the maximum current, or we have to make the graph more sharper. That's why we have to decrease the resistance, and that will affect the quality factor. So quality factor is the factor which will provide more quality for a given resonance circuit. Clear? If resistance will be less, the quality factor will be more, the quality of the output signal will be more in a for LCR circuit. Clear? So this is known as the quality factor, which is depend upon the voltage across the L or C divided by voltage across resistance. Clear? And this quality factor will determine how the clear is the signal is. Okay. So in a given LCR circuit, if we want to change its natural frequency according to the external input frequencies, then we have to change accordingly the capacitance or inductance of the LCR circuit, because you already know the natural frequency omega naught depends upon 1 by root over of L by C. So if we want to change the value of natural frequency of the LCR circuit, we want to change the inductance or capacitance of the given circuit. So in a given LCR circuit, if I want to see a particular channel, it have a particular frequency, so accordingly we have to change the inductance or capacitance of the particular LCR circuit which is connected in the device. Accordingly, the natural frequency matches to the input frequency. So here I am adjusting the L and C so that the input signal omega 3 will match with the natural frequency of the given LCR circuit, so that the frequency omega 3 will get maximum current. Clear? So when we want to change, or further if we want to change the signal from omega 3 to omega 4, then accordingly I have to change the inductance or capacitance of the LCR circuit so that its value will become equal with the omega 4. That's why the omega 4 will get maximum power. Okay. and again if I want to sharp the signal of a particular frequency, if here in this case I want to sharp the omega 3 signal more, then I have to change the resistance of the LCR circuit. So when I want to switch from one frequency to other frequency or one channel to other channel in our television, we have to change the value of capacitance or inductance of the LCR circuit. But if we want to get more clarity in a given channel, then we have to change the resistance of the LCR circuit for that particular resonance frequency. Clear? So this is known as the quality factor, which will determine the sharpness of the LCR or resonance circuit, and this omega naught will determine the resonance frequency of the LCR circuit. Clear? That's why these two factors are used to tune the circuit. That's why these are known as what? Tuning circuit. So in our television we are used one particular switch to, or in our remote there is a particular switch or button that is pressed to change the channel. That means when we press that switch or that button, it will change the capacitance or inductance of the LCR circuit which is connected in the television. Or when we want to change the clarity, volume or the color of a given particular signal or channel, then we have to press another switch which will change the resistance of the LCR circuit so that its quality factor will increase. Clear? So this is how a LCR circuit is used as a tuning circuit, and what is quality factor, and when the LCR circuit will become a resonating circuit or resonance circuit, and what is the natural frequency of a given LCR circuit. Clear? So next we will study what is the power average, and you have to remember this formula. This is the quality factor for a given LCR circuit, and Q value will increase if R will decrease, and this is the natural frequency of a LCR circuit if the output signal frequency match with this one. So there will be a resonance and the circuit will become a resonance circuit. Clear? And these are basically used in the communication circuits to tuning the signals. And this is the graph which shows how the current will vary with different frequencies. So now let us discuss power average calculation in LCR circuit. So what is the power average in LCR circuit? We already know in LCR circuit what is E? E equal to E naught sin omega t, and what is I? I equal to I naught sin omega t minus phi. Clear? So what is P average? P average equal to total work done by total time. But for as I and E both are function of time, so for a very small time dt, what will be the work done? So dw by dt will be give us the instantaneous power, which will be E naught I naught sin omega t into sin omega t minus phi. So this implies you will get the small amount of work done, dw equal to I naught E naught sin omega t minus phi into dt. So this implies we can write this as I naught E naught sin omega t into sin omega t minus phi. It will be sin A minus B. So this can be written as sin A into cos B minus cos A into sin B dt. So this clear? Sin A into cos B minus cos A into sin B. So this can also be written as I naught E naught. Taking this will sin square omega t cos phi minus sin omega t cos omega t sin phi dt. Clear? So this can be written as I naught E naught taking out into sin square omega t cos phi dt minus sin omega t cos omega t sin phi dt. Clear? Understood? Then from this we can write sin square omega t, this term sin square omega t can be written as 1 minus cos 2 omega t by 2, we already know. And here sin omega t into cos omega t can be written as by multiplying 2 and dividing 2. It will be how much? 2 sin omega t into cos omega t by 2. This will be how much? Sin 2 omega t. Clear? So from this equation we can write this implies dw will be equal to I naught E naught into sin square omega t will be 1 minus cos 2 omega t by 2 into cos phi dt, okay, minus this will be 2 sin omega t into 2 cos omega t. So this will be sin 2 omega t by 2 into sin phi dt. So now taking 2 out of the bracket, it will be how much? I naught E naught by 2 into 1 minus cos 2 omega t cos phi dt minus sin 2 omega t sin phi dt. Clear? Okay, will be dw. So now total work done w equal to, by integrating dw, it will be how much? I naught E naught by 2 integration of 1 minus cos 2 omega t cos phi dt, integration over a complete cycle, that is from 0 to t, minus integration of sin 2 omega t sin phi dt, integration from 0 to t. Clear? Okay, so now what will become? So from this we will get what? This is equal to w equal to I naught E naught by 2. Here cos phi is constant, so you can taking cos phi out of the integration symbol, so it will be cos phi integration of 1 minus cos 2 omega t dt 0 to t minus sin phi will be out of the integration, it will 0 to t sin 2 omega t dt. So this can be written as I naught E naught by 2 into cos phi into dt into 1 dt, so it will be integration dt of integration 0 to t will be t minus cos 2 omega t dt, it will be sin 2 omega t divided by 2 omega, limit varies from 0 to t, minus sin phi integration of sin 2 omega t dt will be minus cos 2 omega t divided by 2 omega, limit from 0 to t. Okay, so this will become how much? I naught E naught by 2 into cos phi into t minus, what is sin 2 omega t into t, it will be sin 2 pi which is 0, again sin 0 will be 0, so this complete term will be 0, minus sin phi into cos 2 omega into t, it will cos 4 pi by 2 omega, that is cos 4 pi will be 1 minus 1, so it will be minus 1 by 2 omega. Again cos 0 will be how much? 1, so 1 by 2 omega, 1 by 2 omega into minus minus plus, plus 1 by 2 omega, so this term again will be 0. So we will get what? I naught E naught by 2, this will be t, so cos phi into t, this term will be 0, equal to net work done w. So from this we can write. Clear? as here I am putting t in place of t, it will become how much? 4 pi. So cos 4 pi will be 1. So minus of 2 omega. Again minus cos 0 will be 1, minus of minus 1 will be 1 by 2 omega. So it will get cancel 0, and here it will be 4 pi, sin 4 pi is 0, sin 0 0, so it will become completely 0. So W become E naught I naught by 2 into cos phi into t. So from here we can get W equal to how much? I naught E naught by 2 cos phi into t. So this implies power average will be equal to how much over a complete cycle? Total work done by time. So this implies it will become I naught E naught by 2 into cos phi. So this implies you can write P average for a LCR circuit equal to I naught by root 2 into E naught by root 2 into cos phi. So this implies what is I naught by root 2? It is similar with IRMS, and what is E naught by root 2? It is similar with ERMS. You already know. So the power average for a LCR circuit, series LCR circuit will be IRMS ERMS into cos phi. Clear? This is the power average calculation for what? A series LCR circuit. And from this and here cos phi is known as power factor, and from the impedance triangle we know what is cos phi. If this is R, this is XL minus XC, this is Z, this angle is phi. So what is cos phi? Cos phi equal to B by H, that is R by Z. Clear? And we know what is Z. This implies cos phi equal to R divided by R square plus XL minus XC whole square over. So this implies you can get phi equal to cos inverse R divided by R square plus XL minus XC whole square root over. This is known as the power factor. Okay. So power factor will be maximum when Z will minimum, and when Z will minimum, when XL equal to XC. So in a LCR circuit, if it gets resonant with the external applied EMF, then the power factor will be maximum when XL equal to XC. And what is power factor? This is R by Z, or R by R square plus XL minus XC whole square under root. So from this relation we get P average equal to IRMS ERMS into cos phi. Okay, this is the relation, and here this cos phi is known as power factor, which is depending upon these quantities, and this P average is known as actual power of the LCR circuit, and this ERMS into IRMS, that is V into I. So what is VI? This is also power. This is known as apparent power. Okay, so for a AC circuit, the actual power is equal to apparent power multiplied with the power factor. Clear? So we can write the actual power of a LCR circuit or AC circuit. From this LCR circuit we can calculate easily the power, actual power for any circuit, resistive circuit, inductive circuit, capacitive circuit, RL circuit, LR circuit, any kind of circuit we can calculate by using the RMS value of potential and current, and what is the value of cos phi from the impedance triangle. If there is no inductor, it will become a RC circuit. If there is no capacitor, it will become a LR circuit. If both R and C are absent, it will be resistive. So accordingly we can use the cos phi value. What is phi? Phi is the phase difference between the EMF and the current. So here this is the resultant EMF, because this will be E, this will be VR, this will be VL minus VC. We already studied. So phi is the phase difference between E and I. So accordingly, we using the values of phi and E and IRMS for different cases, we will get the P actual for any AC circuit. So what is power actual for AC circuit? We can write the actual power equal to P apparent into power factor. Okay, you have to remember this. And this power factor will determine the efficiency of an appliance. Clear? If we are using a bulb, okay, which is different 220 volt and having some current rating I equal to 2 ampere. Okay, so the bulb rating is 220 volt and I equal to 2 ampere. So its actual power will be how much? 220 volt into 2. This will be the actual power, but its apparent power will be IRMS into VRMS. So by using the IRMS VRMS, that means if this is the peak value, this is the current. So this will be the apparent value. Because in a AC bulb, the potential mentioned is the RMS value, the current will be the RMS value. So what is the actual value, actual power? The actual power will be this much into power factor. So if the power factor will be more, the apparent power will give us the actual power more close. If power factor is less, then there will be a large difference between the apparent power and actual power. Okay, so if it is a 100 watt bulb and rating is this much, so 100 watt is the actual power, but this will give us the apparent power, and depending upon the power factor we will determine what is the gap between actual power and apparent power. If actual power is completely equal with the apparent power, then power factor will be equal to how much? 1, and power factor become when 1? When XL equal to XC. Clear? But in general circuit, for any kind of appliances, power factor can never be equal to 1, because there are a large number of factors which affect the power factor. But power factor will be more, then the apparent power will be more close to the actual power, and the loss in energy will be very less. So generally the power factor lies between 0 to 1. If the power factor is 0.9 for a given appliance, if the power factor is 0.9 and the actual power is 100 watt, but the apparent power will be 800, then we will get 800 into 0.9, it will be more close to the actual power. Clear? That's why the power factor term will determine how much the apparent power is close to the actual power. And if the power factor will be more, then there will be very less loss in energy. And this power factor determines for each and every appliances in nowadays in form of star rating. Okay, more the star rating in an appliances, we already know that there are different types of star ratings, 1, 2, 3, 4, 5, up to 5 in different alternating current appliances, our AC, TV, fridge, and that star rating responsible for the power factor. More star rating, more efficient, less amount of energy loss, that's why the power factor will be more. Less star rating, less efficient, large amount of energy loss, so the power factor will be less. So power factor is the term which relates the apparent power with the actual power. And what is the value of power factor? Power factor equal to R by Z, Z equal to R square plus XL minus XC whole square under root. Clear? Okay. So next we will study wattless and wattful current. Okay, so you already know in a LCR circuit, if I am drawing the phase diagram, here it will be I or VR, and this will be the for net EMF E, and the phase will be phi. So this is the direction for current I, let it be simply I. This is the direction or phase of I current flowing through a LCR circuit, and this is the direction for net EMF. So there will be a phase difference phi. So we can have two components of I. One is along this direction, that is I sin phi, and one is along this direction, that is along the direction of EMF, that will be I cos phi. Clear? So the current have two components. One component is perpendicular to the direction of EMF, and another component is along the direction of EMF. So from the LCR circuit, we already calculated here that the P average or the actual power will be I RMS E RMS cos phi. Phi is what? The phase difference between E and I. So for the component of I, that is I cos phi, what is the value of phi? Phi will be 0 because this component is lies along the direction of E. If it is I RMS and this is E RMS. So for the component of I RMS cos phi, the phase between E RMS and I RMS cos phi is 0 because both are acting along same direction. So the P average for the component I cos phi, I RMS cos phi will be how much? I RMS E RMS cos phi into cos 0, because here the phi phase difference will be 0. Again the P average for the component I RMS sin phi equal to how much? I RMS E RMS sin phi into cos of, for this component, this is I sin phi, this is E RMS, this is I RMS sin phi. So this is E RMS, this is I RMS sin phi. So for this component of I RMS, the phase difference between E and I is 90 degree. This is 90. So here the cos phi for E RMS and I RMS sin phi will be how much? Cos 90, because the phase difference will be 90. So we will get P average for I RMS sin phi will be I RMS E RMS sin phi into cos. What is the phase difference between I sin phi and E RMS? 90, the cos 90. So this will become how much? 0. So the P average for I RMS sin phi, the component of the I RMS, is 0. So the I RMS has two components. One is I RMS cos phi, which is along the direction of E RMS, and another component which is perpendicular to the direction of E RMS, that is I RMS sin phi. And the P average calculation for the component I RMS cos phi will be this much. Cos 0 is what? 1. So this one I RMS E RMS cos phi, and the component which is perpendicular to this, that is I RMS sin phi, have P average 0. So the total power due to the current I RMS is only because of one component, that is the component which is along the direction of E RMS. That's why this current I RMS cos phi is known as watt full current, and the component of the I RMS which is perpendicular to this, for this it will be 0 power. So this is known as wattless current. Clear? So the component of the I RMS which is along the direction of E RMS is known as watt full current, and the component which is perpendicular to the direction of E RMS is known as wattless current, because the power for the component along the direction of E RMS is I RMS E RMS cos phi, which is the total power, and the component which is perpendicular to the E RMS is 0. That's why this is known as wattless current, and this is known as watt full current. Okay, so the component which is lie along the direction of E RMS is known as watt full current, and which is perpendicular to the direction of E RMS is known as wattless current. Clear? So the I RMS sin phi is known as wattless current, I RMS cos phi is known as watt full current. Okay, so this is all about resistance or capacitance and inductance connect circuit or LCR circuits connected in series for AC source. what is the power average calculation, what is quality factor or Q factor for a LCR circuit, when the LCR circuit will be called as a resonant circuit, what is the natural frequency of a given LCR circuit, how we can tune a signal by using LCR circuit. Okay, understood? So next class we will discuss further in alternating current. Okay, thank you.